I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 16, Clusters, Quasars, and Dark Matter. In this lecture, we'll begin to investigate the greater structure of the universe and uncover one of the great mysteries of modern astrophysics. One of the common themes of astronomy is the notion of structure. As interstellar gas forms into stars, and the stars begin their process of nuclear fusion, we've discussed in our studies of astronomy that layers of hydrogen and helium burning shells develop. And so that as we look at a star and sort of take a view of its cross-section with the corona and the chromosphere and the photosphere and the convective layers and so on, we find that it has structure. We also recognize our solar system as a structure where mass in orbit around the sun coalesces into planets and the other bodies of our solar system. And beyond our solar system, we recognize that our star, the sun, is only one of a very large number, hundreds of billions in fact, of stars that move together around the common galactic center, which is the supermassive black hole Sagittarius A at the center of our galaxy. So a galaxy is a form of structure, the way stars collect together. And in our last lecture, we talked about the classification of galaxies and how different types there are and so forth. But another greater structure of our universe that is of great interest to astrophysicists today in the subject of astronomy that's known as cosmology is the fact that the galaxies in our universe are not uniformly distributed throughout all of space, but in fact form clusters. Using the Hubble telescope, we're able to identify many clusters nearby. For example, say clockwise, starting in the upper left of this diagram here, we have the Hickson cluster, the Fornax cluster. In the bottom right, the Coma cluster, and in the lower left, the Virgo cluster. These are all clusters of galaxies in our interstellar neighborhood. And using our distance standards, some of which we've discussed already and some of which we'll discuss in the next lecture, we've been able to determine the arrangement of galaxies in our local group. So here's basically a three-dimensional plot. Notice the scale in the lower right depicting 100 megaparsecs, 10,000 parsecs in a megaparsec. So these are fantastically large distances, and the bubbles that you see here on the diagram are regions in space that are highly populated by galaxies. That immediately means that the regions in between that are not identified are actually voids in space. Right in the center of the diagram, you'll see a dot signifying the local group, which is our local group of galaxies, which is technically considered to be part of the Virgo cluster. Cosmologists have identified, and observational astronomers, of course, have identified this structure and looked particularly, or we can look very carefully at our local neighborhood of galaxies to find that there is structure to the way galaxies organize themselves. It's not such an obvious structure as the layers of stellar evolution or the simplicity of a solar system or even the orbit of stars around the center of a galaxy. Nevertheless, there are regions in space where there is a great collection of galaxies. We see at about a distance of 100 megaparsecs, where the Coma cluster and other clusters of galaxies are referred to as the Great Wall in space. And we can also identify voids where there is very limited population of galaxies. This this universal structure of galaxies is to this very day not very well understood. Cosmologists and astrophysicists are currently working to create computer models based on observations and very good theoretical physics to predict the structure of the universe, and a great deal of progress is being made. But as better and better astronomical measurements are made, cosmologists are forced to revise those theories and tweak them. And ultimately, the hope is that the observational astronomy that we do will asymptotically approach our theoretical models, and we'll begin to understand the mechanism behind structure in our universe. An interesting fact that you may be aware of from your own studies of astronomy and may have seen pictures like this one before is that there are regions in space where galaxies are sufficiently densely populated that they can in fact merge. There are many instances of irregular galaxies that are believed to be the result of two galaxies passing through each other. And there are also instances we can see where very clearly two galaxies are interacting. Here we can see the spiral galaxy that is to the left has a very clearly identifiable nucleus, and that there is another spiral galaxy to the right of it. A smaller galaxy, certainly with fewer stars and with a less defined nucleus, but nevertheless, taken independently, these two galaxies we would identify as individuals. In such close proximity, though, they exert gravitational forces on each other, and it's obvious that the nucleus of the one galaxy and the nucleus of the other galaxy can strongly interact and exert a gravitational force of attraction. This ultimately will cause these two galaxies to merge, and in fact, they can merge to the extent that there's even that they're no longer distinguishable as two separate galaxies. As this happens, the mass of the one galaxy and the mass of the other galaxy become combined, creating regions of space where there's a very high density of material. That material is available for star formation. Indeed, the increased density inside of these galaxies as they coalesce or merge is going to create a profusion of new stars in the interaction. Ultimately, what can happen as well is the nuclei of these two stars will merge. Now, it's generally believed, and is good theoretical and observational basis for the fact that at the center of galaxies are typically supermassive black holes, and that as these two objects come together, those two super black holes will merge to produce what? An ultra black hole, a galaxy of enormous size, at its center, a black hole fantastically massive. There's an end result to this natural process that's going on in the universe of galaxies merging and coalescing, and that is active galaxies. It is possible, and in fact we've observed that it happens, that galaxies in our universe can merge, coalesce, more material is brought together, so that the supermassive black hole at the center of the galaxy is so massive that it's that the accretion disk around the black hole at the center of the galaxy, the accretion disk is the material that's being drawn into the event horizon of the black hole. That accretion disk begins to emit radio waves and X-rays with fantastic intensity, making a galaxy of this type much more luminously intense than ordinary galaxies that have much lower masses and have not been the subject of mergers. These active galaxies stand out in our universe even when they're extraordinarily far away. In fact, the first active galaxy that was discovered was first believed to be a star because based on its luminous intensity, the distance to it is judged with the notion of it being a star. If a star were to have that luminous intensity, it would have to be much, much closer. But the spectrum of the thing was not quite like one would expect from a star. It was sort of quasi-stellar and very, very suspicious. Thus, the name quasar was, which is quasi-stellar, or is based on that, the etymology of it, was the name first given to active galaxies. But the telling thing comes when the redshift of the galaxy is measured. Remember that when luminous objects in our universe are moving toward us, they are blue shifted by the Doppler effect, and as they recede from us, they are redshifted. The redshift is quantified by what is known as the redshift factor. It's represented by a lowercase z, and so you may see that in some of the literature that you study with regard to this astronomy. Suffice it to say, the first quasar that was identified had a redshift factor z of 0.15. It was a little tricky to figure this out because so redshifted was this original quasar that At first, even the spectral lines of hydrogen couldn't be identified because they had been shifted over further than anyone had imagined possible. In fact, the redshift associated with this particular quasar, when compared to Hubble's law, and you recall Hubble's law is the law that predicts that the further an object is away from us, the faster its recession. Hubble's law predicted that this redshift had the object, this new quasar that was discovered, traveling at 15% the speed of light away from us. In order for that to be true, according to Hubble's law, it would have to be 2 billion light years away. So immediately, based on the luminosity, we recognize that this is an object much, much larger than a star. It's in fact an active galaxy, commonly known as a quasar, 2 billion light years away from Earth. The immediate revelation about that is that in order for an object to be sending light from us from 2 billion light years away, enough time would have passed, 2 billion years in fact, for light to traverse that distance. So this quasar is 2 billion years old. That immediately sets the age of the universe at 2 billion years, because the thing has been in existence for 2 billion years for it to be possible for the light to have arrived at Earth. Since that first quasar has been discovered, more and more quasars have been discovered. Benefit of having a Hubble Space Telescope. And in the Able cluster of galaxies, a quasar has been observed, the furthest object ever, about 13 billion light years away. That means that our universe is at least 13 billion years old, according to current estimates, and that is in fact how the age of the universe is determined. By galaxies that have coalesced and become so massive that their supermassive black hole cores emit strong radio and X-rays with fantastic luminosity that can be measured at great distances by astronomers here on Earth to predict not only the age, but also the size of our observable universe. We've already mentioned, or I've already mentioned in this lecture, that galaxies can coalesce, and we saw a striking picture of two galaxies, one right on top of each other, in a dramatic collision interaction. I forgot to mention, and this is bad form, I was supposed to say when we were looking at that slide, that although it's very dramatic, galaxies colliding when they're right on top of each other, the galaxies themselves still have a density that makes individual stellar collision remarkably unlikely and uncommon. Surely it happens in our universe that stars collide, but when one galaxy passes through another, there's enough distance between the stars that they miss each other in terms of collisions, but of course the gravitational interactions are quite strong. But here we have an image of two, technically three galaxies, M82, M81, and NGC 3077. And in this image, as we look at them, we would say, well, they're hardly interacting at all. And in fact, we have to respect the fact that it's a photograph and that there could be great distance between these galaxies and that there's no reason for them to be interacting. But in fact, they are strongly interacting with each other, and based on information gathered from the X-ray imaging of this region in space and the interstellar dust, we find that in fact the region of space in between is not as empty as it might seem. This is one small piece of evidence that we have for the notion that the space between galaxies is filled with matter that we cannot see. Matter that's not luminous is inaccessible to astronomers because we cannot see that which does not send light to our telescopes. That matter in the universe which does not produce light is therefore referred to as dark matter. It doesn't mean that it's some special kind of oozy, strange matter that doesn't appear on the periodic table. In fact, it should be, in every sense, conventional matter. But being non-luminous, we give it the name dark matter. There are essentially three pieces of evidence that we rely on to validate our suspicion that the universe has a great deal of dark matter in it. And the first is the galaxy rotation curves. The force of gravity between objects in our universe is well understood since the time of Newton. There's a mutual force of interaction that diminishes as 1 over the square of the distance. And that force law can be used mathematically to describe completely, with very little error, the motion of the planets around the sun. If you think of our galaxy with its supermassive black hole in the center and all of the stars orbiting about it like planets, then that system should work the same way. Indeed, it's true that there are a lot more objects involved than there are in our solar system, but the fundamental gravitational force between them remains the same. And so our galaxy goes around with our sun traveling about 230, kilometers per second, taking about 230 million years to make the circuit. It does so under the influence of the gravitational force, and astrophysicists try to predict whether that velocity is the appropriate one. But based on the motion of our sun around the center of the galaxy, and also the motion of stars further and further out on the disk, recall that our sun is about half the distance to the center of our galaxy, and all of that mass outside, in terms of its rotation speed, the rotation speed should drop off and drop off and drop off. Objects that are distant from the sun, for example, Pluto, orbit the sun at very, very slow speeds. The further you are away, the slower the speed should be. And so what we expect is a kind of Keplerian motion, labeled here on the diagram, is named for Johannes Kepler, who first described the motion of the planets around the sun from experimental data. But we expect the speed to be less and less the further you get away from the galactic center, but experimentally we recognize that that's not what happens, in fact. As you go further and further from the center, stars are orbiting the center of the galaxy at higher and higher speeds. The only explanation that astronomers currently have for this effect is that there must be outside of our galaxy a quantity of mass twice as great as the mass of the visible galaxy itself. I say visible galaxy because there's no visible evidence of this mass being outside of our galaxy. Therefore, we must assume that it's there, but it's just non-luminous, so we can't see it. We must assume that that mass is dark matter, because based on all of the matter that we can see, we cannot explain the rotation curves of the galaxy. The second piece of evidence is cluster interactions. When we look at galactic clusters, or clusters of stars, and the way that they interact with each other, we have a group of stars in a certain location. In order for them to be held together by gravity, there has to be a certain amount of gravitational force available. And so we look at a cluster and we say, well, there's a certain amount of luminous material here. We estimate the size based on what we can see, and also we can estimate the velocities, and we discover that the velocities of the objects involved in the cluster are too great for the gravitational force of the visible available mass to account for. And so it's believed that the space in between these objects is full of dark matter, and that dark matter increases the gravitation and allows for cluster interactions in our universe. The third evidence for dark matter is, I think, by far the most interesting, and its effect, known as gravitational lensing. The gravitational lensing is due to a notion that is an important aspect of Einstein's general theory of relativity, and that is that space-time is curved by the presence of mass. And in fact, the effect of gravity itself is now interpreted in our modern understanding and savvy as the curvature of space-time. And objects that are moving through our universe curve from their straight line motions because they are following the curvature of space-time that naturally occurs in the vicinity of mass. So an interesting effect takes place, which is known as gravitational lensing, where the curving of space-time bends the path of light, because light follows the curvature of space-time in the same way that mass does. This is maybe a little bit difficult for you to come to terms with, because there's generally a notion that lasers, for example, travel in straight line paths. I can go to the hardware store and buy a device known as a laser level, which shoots light out in all directions and in principle gives me a perfect line, because light beams don't curve according to gravity. If I were to stand in the middle of my room and throw a piece of clay at the wall, by the time it hit the wall it would have dropped under the influence of gravity, and I believe that laser beams don't do that. The fact of the matter is they do. It's just that their curvature is very, very small, because the laser light is traveling at the speed of light, and so it doesn't deflect much. It's like the difference between me throwing a bullet and shooting a bullet out of a gun. The bullet shot out of the gun travels in a straighter line because it's higher velocity, and so light appears to travel in a straight line. But the reality is that when light is produced by a distant object and comes to our telescopes here on Earth, that it follows the curvature of space-time and bends. Now, the mass is distributed not uniformly, but completely throughout all of space. And so the bending of light is continuous. It's not just over here and over there, it's everywhere. And the bending of the light can manifest itself in patterns that are not unlike the way a ground piece of glass, that is, a lens like you would have in your glasses, or a magnifying glass, or indeed the lenses that are in an optical telescope, that the way that lens redirects the light, changes its path. It turns out that gravity does the same thing. On the upper left-hand image here, we see an elliptical galaxy in the foreground that is gravitationally lensing an object that's behind it. In fact, these 4 blue dots that you see surrounding it are believed to be an image of the same object. And I say believed to be, but there's strong experimental observational evidence to support that, because you look at the spectrum of those objects and they're identical, therefore suggesting that it's an identical object. The photograph of the lower right, I'm going to ask you to look at that photograph and see if you can see, if your mind can identify a sort of circular pattern that one might see looking through a piece of scratched glass, and how that produces circular patterns, sort of swirls that can be observed. In this image, I think if you look at it, you'll see like a sort of circular nature to it, and that circular nature is the gravitational lensing. So it's not a problem. You look at gravitational lensing, you say, well, there are stars there and galaxies and whatnot, and they bend the path of light. But it turns out that in order to correct these images for the gravitational lensing effect, we have to allow for the existence of greater quantities of mass than are luminously visible in the image itself. That is, there would have to be some sort of dark matter in the space in between in order to account for all of the gravitational lensing that's going on. As a side note, the gravitational lensing is useful to us because earlier in this lecture I mentioned an object which is over 13 billion light years away. That object would be invisible to us were it not for gravitational lensing, which makes it appear closer than it actually is. But nevertheless, these are the 3 very, very strong pieces of evidence that we have to suggest that our universe is filled with dark matter. In fact, the idea is that there's 10 times more dark matter in the universe than luminous matter. The next question becomes, if the universe is filled with dark matter, what actually is it? I mean, what constitutes the dark matter? There are basically 4 explanations for this, 3 of which are material in nature, and another one is a little bit more exotic interpretation of modern physics. Nevertheless, here's the list. The first is neutrinos. We recall that at the core of our sun there are nuclear reactions going on, and as those nuclear processes take place, one of the products are neutrinos, sometimes referred to as solar neutrinos. These particles are very, very weakly interacting. They don't interact with much of anything at all, and there's a profusion of them in space as a natural byproduct of nuclear reactions taking place. Could it be that they are the dark matter candidate? Well, the general feeling is that their mass in the universe is too small to account for all of the dark matter in the universe, but they're certainly not luminous, and so their mass at large cannot be accounted for. This brings us next to the notion of WIMPs, which is weakly interacting massive particles. The idea here is that there's a kind of particle that we just haven't found yet, that's so weakly interacting that it's difficult to build any kind of detector that would pick them up. And yet they're very, very massive. And so they have a gravitational influence all throughout space, but we really just can't detect them. It's not just because they're not luminous, but even at that, they're so weakly interacting that we haven't detected them yet. And there are some experiments going on to try and detect these particles based on some theoretical properties that they may have. But currently, WIMPs, at the risk of offending somebody somewhere, I think is a bit of a long shot. Another option is machos. There's a fun name. This is massively compressed halo objects. And the idea here is that in the halos of galaxies, remember that a galaxy, even a spiral galaxy like our own that is luminous as a flat disk, has an entire spherical region encompassing it where there are very old stars, potentially many of them so late in their life cycle that they're no longer luminous. They're very highly compressed, dense stellar objects that simply aren't producing light, but have a fantastic amount of mass. This is believed to be a very, very good candidate for explaining the rotation, the problem of the rotation of the galaxies, because those halo objects are very, very close in proximity to the galaxy itself, and so a good candidate for influencing that motion. Not so much for the interactions of galactic clusters or gravitational lensing overall. Particularly because even if you include any invisible mass of halo objects in clusters of galaxies, their dynamic behavior still needs additional mass on top of accounting for say 10 times additional dark matter in each of the galaxies participating. You still wouldn't have enough mass to explain it. Another thing that's going on currently is the notion that the gravitational interaction needs to be modified. The idea here is that it's not the mass in the universe that's out of whack, but it's in fact the way that we measure the gravitational force, and that on cosmological distances, the gravitational interaction between the luminous matter that we can see may be greater than theoretically predicted by Newton's laws. The notion is that we need a better theory of physics to describe that gravitational interaction at long range. Currently, the best candidate for that is what is known as the string theory. The string theory predicts that the gravitational interaction is caused by the exchange of particles known as gravitons. The really fun thing is that these gravitons are not constrained to live in our universe of 3 dimensions, that there are multiple dimensions available to the particles, the graviton particles, and that they periodically can pop out of our 3-dimensional universe and pop in again at much greater distances, and it changes the strength of the gravitational interaction so that at large distances the gravitational force is theoretically stronger than it would be if a Newtonian prediction was used. Currently, fantastic amounts of research is going into validating the string theory because it currently has no significant experimental validation of its own. In the news just this past year, the Large Hadron Collider in Europe was activated and unfortunately malfunctioned, and coming in the September of 2009, they're predicting that once again they'll make an attempt to measure the Higgs boson, otherwise known as the God particle. And if that happens, then it'll lend a great deal of support to the string theory as a legitimate theory of the universe, and therefore make its predictions about the gravitational interaction at long range much more legitimate. So this issue of dark matter in our universe remains an open question. So far as the composition of the universe, what we can tell, what we can see is going on, this is the way it breaks down, and it's rather remarkable. About 0.4% of the universe is stars and everything else that we see. All of the stars in the universe, that's right, those hundreds of billions of stars and those hundreds of billions of galaxies that we've been looking at with the Hubble telescope, constitute about 0.4% of the universe at large. 3.6% of the universe is the intergalactic gas, not the stars, but everything in between. And you can sort of accept that because that's where the stars come from. The coalescence of gas in our universe and star-forming regions creating new stars in an ongoing process. Dark matter vastly outpopulates if we use dark matter in all the situations where we need it to explain galactic rotation and the behavior of globular clusters, galaxies, and so on. 23% of the universe would have to be composed of dark matter. The other 73% of the universe is composed of dark energy. Now, an immediate argument that should pop into your mind is that it's strange that energy should be mentioned in the same pie as matter. All we need to do to get around this for the moment is to remember that Einstein gave us a mass-energy relationship, E equals mc squared, an equation that tells us that matter and energy are equivalent and proportional to the speed of light squared. And so mass and energy in the universe are, and their fraction is an important part in the science of cosmology, the science of the structure and evolution of our universe, a science that we'll discuss in more detail in our next lecture.